Have you ever wondered where stars come from? In the vast expanse of the cosmos, the birth of a star begins in places known as nebulae. These nebulae are not empty voids, but rather grand reservoirs of cosmic dust and gas. Over time, the nebula's own gravitational force starts to pull these particles together, forming clumps of matter. As these clumps grow, they pull in more and more matter, creating an ever-growing ball of dust and gas. This ball, now known as a protostar, continues to grow and condense. As it does, the pressure and temperature at its core start to rise. Now here's where the magic happens. Once the core temperature of the protostar reaches a staggering 10 million degrees, a process known as nuclear fusion begins. This fusion is the heart and soul of a star. It's where hydrogen atoms are squeezed together under immense pressure to form helium, releasing an incredible amount of energy in the process. This energy, in the form of light and heat, pushes outward against the inward pull of gravity. When these two forces balance each other out, the protostar has reached the stage of its life cycle known as the main sequence, and a star is officially born. This newborn star with its nuclear heart begins to shine, casting its light across the cosmos. It's a beautiful, fiery beacon in the dark expanse of space, a symbol of life amidst the cold void. And so a star is born, lighting up the cosmos with its brilliant glow. Once a star, what's the next stage in this celestial journey? Well, let's dive right into it. The star now enters a phase known as the main sequence, which is essentially the star's adulthood. This is where a star will spend the majority of its life, just like our very own sun. The main sequence is a stage of stellar evolution where a star fuses hydrogen into helium at its core. This process is called nuclear fusion. And it's not just any process, it's the powerhouse of a star, providing the immense energy that makes a star shine. Now imagine the sheer scale of this energy, so vast that it lights up the cosmos and supports life on planets like Earth. But not all stars are created equal. Oh no. The size, color, and temperature of a star during the main sequence phase depend primarily on its mass. Let's take a red dwarf, for instance. These are stars with a lower mass, so they're smaller, cooler, and have a reddish hue. They're also the most common type of star in the universe. On the other end of the spectrum, we have blue giants. These are stars with a higher mass, and therefore they're larger, hotter, and have a bluish color. They're also much rarer than red dwarfs. But regardless of whether a star is a red dwarf or a blue giant, the main sequence is where it truly shines, pun intended. So the main sequence, in a nutshell, is the prime of a star's life. It's the stage where a star is at its most stable, balancing the forces of gravity pulling inward and the pressure from nuclear fusion pushing outward. It's a star's heyday, if you will, where it shines the brightest, radiating energy out into the universe. But remember, just like everything else in the universe, stars too have a lifespan. And the main sequence is just one part of this fascinating journey. But that's a story for another scene. For now, let's take a moment to appreciate the energy and beauty of stars in their prime during the main sequence. The main sequence represents the prime of a star's life, where it shines the brightest. But what happens when a star runs out of hydrogen fuel, you may wonder? Well, a star's life doesn't end there. Instead, it goes through a fascinating transformation, morphing into either a red giant or a white dwarf, depending on its mass. When a star depletes its primary hydrogen fuel, it begins to fuse helium. This fusion results in the production of heavier elements like carbon and oxygen, causing the star to expand dramatically. This massive, bright, and somewhat cooler star is what we call a red giant. Our own sun, a rather average star, will eventually swell into a red giant, engulfing the inner planets, including Earth, in its outer layers. Red giants are not just bigger, but they're also brighter, shining thousands of times more brightly than they did in their main sequence. They continue this helium fusion phase for a few million years, a blink of an eye in cosmic time, before their cores contract, and their outer layers are expelled into space. On the other hand, let's consider low-mass stars, those less than about half the mass of our sun. These stars lead a somewhat different life. As they exhaust their hydrogen fuel, they don't have enough gravitational pressure to ignite helium fusion. Instead, these stars shed their outer layers, leaving behind a hot, dense core known as a white dwarf. White dwarfs are fascinating celestial bodies. They are incredibly dense, packing a mass comparable to the Sun into a volume roughly the size of Earth. While they don't have the fuel for nuclear fusion, they continue to shine for billions of years thanks to their stored thermal energy. So, whether they balloon into red giants or shrink to become white dwarfs, stars continue their existence in the cosmos. They may no longer be in their prime, no longer fusing hydrogen in their cores, but they continue to shine, continue to dazzle us, and continue to be significant players in the grand cosmic theater. Whether they become giants or dwarfs, stars continue to captivate us with their celestial dance. How does the captivating tale of a star end? Picture this: a high-mass star, having exhausted its nuclear fuel, collapses under its own gravity. The core implodes, sending shockwaves coursing through the outer layers of the star. These shockwaves trigger a cataclysmic explosion that we call a supernova, a dazzling display of stellar fireworks, illuminating the cosmos with energy that can outshine entire galaxies. In the wake of this celestial spectacle, something extraordinary happens. Depending on the mass of the original star, the core that survives the supernova can transform into one of two incredibly dense objects: a neutron star or a black hole. Neutron stars are the smallest and densest stars in the universe, with a teaspoon of neutron star matter weighing about 1 billion tons. Imagine that. A star, once millions of miles in diameter, collapsed into an object just about 12 miles across. Now, if the original star was even more massive, the core implodes to a point of infinite density, creating a black hole. These cosmic behemoths have gravitational pulls so strong that nothing, not even light, can escape their grasp. Speaking of black holes, did you hear the recent news? Scientists have captured the first image of a supermassive black hole, Sagittarius A*, at the center of our Milky Way galaxy. This monumental achievement, brought to us by the Event Horizon Telescope, is a testament to the wonder and mystery that black holes represent. It's a glowing ring of red, yellow, and white surrounding a darker center, representing the black hole's shadow or silhouette. Our understanding of these celestial phenomena is still in its infancy, but every new discovery brings us closer to unraveling the mysteries of the cosmos. From a spectacular birth to a dramatic end, the life cycle of a star is a cosmic journey like no other. Indeed, the death of a star is not an end, but a transformation, a testament to the cyclical nature of the universe. But is the death of a star really the end, you may ask? Well, not exactly. You see, the cosmos operates on a cycle of birth, death, and rebirth, much like a phoenix rising from the ashes. When a star meets its end, it doesn't simply vanish into the void. Instead, its death throes fling its constituent elements far and wide across the universe. This stellar debris, the remnants of a once majestic star, then seeds the cosmos with the raw materials needed for the birth of new stars and planets. Heavy elements like carbon, oxygen, and iron, which were forged in the heart of the dying star, scatter across the heavens, enriching the interstellar medium. And so the cycle continues. These elements, once part of a star, may coalesce to form new stars, planets, and perhaps even life. It's a cosmic recycling program on a grand scale, a testament to the endurance and adaptability of matter in the universe. The death of a star, therefore, is not an end, but rather a transformation, a change of state. Its matter, energy, and the elements it created are not lost, but instead, they are given a new purpose, a new role to play in the grand cosmic theater. So the next time you gaze upon the stars twinkling in the night sky, remember this: each one of them, each speck of light, is part of a grand cosmic cycle of birth, death, and rebirth. And in this grand scheme, the death of a star is not a finale, but rather an intermission, a pause before the next act. In the grand cosmic theater, the end of a star is but a new beginning. So we've journeyed through the life of a star, from birth to death and beyond. We've seen how stars are born in nebulae, live out their lives on the main sequence, swell into giants or shrink into dwarfs, and end their lives in supernovae. Through understanding these cycles, we've glimpsed the grand cosmic cycle, the ebb and flow of matter and energy that shapes our universe. Remember, each star's story is a piece of the larger cosmic narrative. If you enjoyed this cosmic journey, don't forget to like, comment, and share this video. Stay curious and keep exploring the stars.